So the problem says that a satellite is in a circular orbit of radius r. So if the satellite is here, the orbit's radius is r, that's there, and the area enclosed by that is a is equal to pi r square, which is fine by the orbit. And we need to determine few things, how r is how these things are related to r. That's what we need to find. Number one is period, then kinetic energy, angular momentum, and speed. So when we say period, we can apply Kepler's law. So that is t square over r cube is equal to 4 pi square over gm. So all of these are constant because this is the mass of the center object around which the satellite is orbiting. So t will be equal to t square is r cube times 4 pi square over gm. Now if this is constant, the whole thing is constant of course, so then t becomes, so we can say t square is proportional to r cube. So t is proportional to r to the power 1.5 because r to the power 3 over 2, which is 1.5. So that's there. Then we need to find how it's proportional to kinetic energy. So we know kinetic energy is gmm, so m being the mass of the center object and lowercase m is the mass of the satellite, divided by 2r. So this is kinetic energy. So kinetic energy now becomes proportional to 1 over r basically, because gmm over 2, this is constant, so this is the proportionality, or we can say k is proportional to r to the power minus 1 basically. Sorry, this, let's use lowercase r. I forgot I used uppercase r because that's what the radius is, so like that. Then we need to find angular momentum. Angular momentum we can write here, angular momentum is I don't know what I wrote. Angular momentum, that one is m omega r, that we know. That's what angular momentum is. Now omega is 2 pi r over t. So t is the period and this is r again. So we can say angular momentum is becoming m times 2 pi r square over t. Now if we go into proportionality, we can see clearly that this is constant, and t we don't have to write the total exponent because we are trying to find only the relation, only how it changes with r. So how is it dependent on r, how, what's the proportionality with r, that's what we want to find. So what we can do here, we can just write like that, this is r square, and if we recall, t is proportional to r to the power 1.5. so we can just write that there. I will write a little bit lower, so that's there. So this is now becoming, sorry, I started writing actually, that's why. So this is r square, sorry, r square, and this is r to the power 1.5, that's proportional, and we are saying, which is of course 2 pi m is constant, and of course when we are saying t is proportional to, that's why we have written proportional. But if we wanted to write equate, we wanted to equate it, we could have said this is constant, that's why. So now the proportionality becomes r to the power 0.5. so that's the proportionality of angular momentum with r. That's the relationship, that's how angular momentum changes with r, we can say. Finally we need to find speed. Now we already found the relationship with kinetic energy, which is r to the power minus 1. We know that kinetic energy, speed is kinetic energy is square of speed, basically proportionate. So if we want to say speed, how speed changes with kinetic energy, that will be square root of kinetic energy, because kinetic energy is of course just half mv square. So v is equal to 2 kinetic energy over m square root. That's how we can relate kinetic energy with velocity. So if we want to write proportionality, that will become, when 2 and m they are constants, so that will be like that. Velocity is proportional to square root of kinetic energy. So that we are writing. Now we know how kinetic energy is affected, how kinetic energy is related to r, which we already found, which is r to the power minus 1, which is 1 over r basically. So this is becoming 1 over r proportionality factor, which is of course we can write 1 over r to the power half, or proportionality is 1 over r to the power 0.5, or we can just write r to the power minus 0.5. So that's how speed will change with respect to r, or that's how speed is dependent on r, however we state it.